till
Till
at least
20
the end
days.
of
the
this
end of the
semester.
semester.
No,
Yeah.
sir.
Okay, and you
For
can
20 days.
download also, no?
Yeah, we can download.
120 days, huh?
So 20 days only. Like if we are recording it today on 22nd, then it will stay up to like 12th of November.
Okay, so what are you guys doing? You're downloading it and keeping for your reference?
Yes, sir. We just uploaded it on the drive for everyone.
Hello?
So we've maintained a
So
batch-wide repository, so we upload all stuff over there.
okay. But it would be a huge repository, because so many recordings. So how do you do? So some central pool kind of a thing, some Google
So
Drive
Infinite
kind
has
of, or
given us 1
OneDrive.
terabyte of storage, so we consume that for this.
Cool. Quite interesting. Okay. Let me check. Okay. Okay, guys, then let's restart or do a memorizing exercise. Where were you? Sorry, this is my kids' business. Let me close this down. Okay. Okay, so we were trying to understand the closed loop control system with complete components, okay, which means that everything. So if you look at the architecture, okay, so it contains various components starting from here. Maybe if you want, give me a minute. Okay. So it starts with a set point. Okay, so you have to have a conversion mechanism to take the set point inside. So this is YSP. This is original YSP. Then you need to have a converter that takes, which is equivalent to mostly the measurement conversion. So this would now go into YSP tilde, which is the set point in terms of signal. So this is the physical variable. This is the signal equivalent. My goodness, so this guy is making an issue. So let me use this to say explain that. So this is the signal equivalent. So then that is going to the comparator where you would get the measurements and you calculate the error. Okay, and that error, of course, in terms of the signal, is going into the controller. Controller would send it to I2P. Okay, and from I2P, I think we have a very detailed comparison. Okay, from I2P, it is going to I2P means I means current, P means pressure. So current to pressure converter or current to pressure transducer whatsoever. Then that is connected to the control valve, and control valve is connecting back to the process. So this is the overall mechanism. And so our concern was, okay, so we are basically looking for a process. So we know that we need to control the process at certain set point. So in fact, so see, the key interest comes in, of course, the process term would be there. There is a controller term is there because you have to control the process. And the rest all are added up based on the needs, because the controller require measurement, so you need to add a sensor. Okay, the controller will only take error in terms of signal, so you probably would have added a signal converter followed by a comparator. Then of course the real controller stays as it is. Then controller gives you an output, so you will have to go back and convert them into pneumatic variable, because your final changes which is affected through a control valve, or by that means any actuator. Okay, so this control valve, so see what I am trying to say, just for controlling the system you have added up and bulked up the entire overall system in a slightly larger fashion. So the point is, your aim is to just control, but you have added too many things. So our question is whether this added system making the system worse, or uh, so see, so your closed loop control system contains a lot of components, and all of them are interacting each other. So the point here is whether such interaction, because see, you are not looking them in isolation. We are looking at the entire business, starting from, okay, the converter. So as I told, this is the set point, this is the YSP tilde, okay, the comparator, okay, controller, I think maybe GC output, okay, then you have your GI to P, okay, then you have your GP, so after which you would have a disturbance coming in, maybe I will write it as GD, getting added up here, this plus here, this is your original output. And you have a measurement here, which is GM. You can also write GM here for consistency, and this is coming back, this is plus, and this is minus. So many of the things that you see here is slightly unwanted, but in terms of it, what you call, in terms of it, it's implement, in terms of it, the general structure, but for the implementation purpose, you have added so much of things, because something needs something downstream, something needs something upstream. So our idea, so why we are looking this overall closed loop control system, to just to know whether this additional component has made the system destabilize or what. So it's like this, right? You have added too much of a thing and make this overall system bulkier, whether it would make the purpose good or bad. So to that extent, we started looking at two types of controlling strategies you want to look at. One is servo. Okay, the other one is generally called as regulator. Servo is also known as tracking problem. Okay, so these are the two classical problems. Wherever you go, you will have to deal. Other one is disturbance reduction. So what is the difference between servo and regulator? Okay, in the servo case, okay, so for instance, you are going to control a CSTR or whatever, okay, and you wanted to increase the temperature. So this is YSP for, let's say this was your original YSP. And that time t is equal to 1, you had to increase it. Step up or whatever, assuming stepping is the simplest option. You have to increase it. So this become YSP1, this has become YSP2. Okay. So this is because, let's say this will become 80 degrees. So at that moment, you have been told that increase the temperature of the reactor to 100 degrees. So this for better conversion, better performance, so on and so forth. Okay, so the idea here is, this is of course the set point. Your original process may be slightly fluctuating this, oscillating around this because of the noise, so on and so. There are various controlling factors. So you should be able to track this change. So essentially means that you may not be able to track it immediately. So you may be able to do a job like this. So your original process variable. So this is your ym, which is the measured output, or y, whatever you call. It should be able to track the measured set point. So it goes up and captures. So this is the typical servo problem, or known as tracking problem. Tracking problem is classic. So you do missile tracking. This is the same problem. You have your target. Okay, so your target is moving, and maybe, or you would have a target and it is changed. It's deviated the target. So your missile has to intercept it. So this is, as I told, controlling process control is just not control. No? It is a universal subject. So for the chemical process control, this is like a step change in temperature, pressure. But in tracking problem, it's a classic problem. You are tracking a missile target, or even that sense. So see, our aircraft, you see. So aircraft, you see aerospace applications. So let's say you are traveling in Boeing 787, whatever, Airbus 320, whichever. So they, how do they do? So most of them are operating in autopilot mode. Most, just after takeoff. Of course, takeoff and landing is manual. So this is most of the time their aircraft would be in autopilot mode. So how do they do it? So autopilot should know, you will know the, you have this target trajectory. Let's say if you are going from Delhi to Mumbai, you know the GPS coordinates exactly, lat long, in which the aircraft has exactly need to be followed to reach Mumbai. Of course, the deviation will come if something comes in the middle. So there, the pilot would intervene. Otherwise, this is the path that the aircraft has to follow. So the tracking problem for that aircraft, of course, they use a lot of PI, PID and control. So the same thing, but more advanced in terms of the robustness and things like that. You cannot compromise on the margin. So you would have to follow this. Your aircraft may be following like just trying to uh, follow this line. Okay. So if it diverts, it has to come back to this line. Sometimes you forcefully divert. Let's say some other aircraft in the line, you will have to move up. So that is the disturbance here. So you have to reject that disturbance. So there is, let's say within, I think it is 30 feet, I guess, within the vicinity of the 30 feet or 300 feet, I don't know, 300 feet, if there is one more aircraft, they'll have to kind of replant their trajectories, at least for some time. It may go, so one of the aircraft might go up and one of them might go down. For some time, then they would come back to their original route and it would continue to travel. So if you are traveling in this direction and you find one more aircraft on the line and you are deviating from the trajectory, that is a disturbance because one more aircraft is there and it can kind of hit you and make things worse. You identified that disturbance and rejected that disturbance. So in context of chemical process control, it is like this. Okay, you have your YM. So this is only YM. There is no tracking at the moment. You are perfectly tracked, assuming that. So this is your YSP. Oftentimes it would follow exactly. So let me just say. It is following exactly. Okay. So let's say this is your reactor and you wanted to measure. So your temperature you are controlling. Fine. And what is the rejection? So here, how do you control? You might put a cooling water. Okay, cooling water line you add, and based on this temperature in the cooling water, you would control the tank temperature. Sometimes suddenly, because this would go to a surge tank, right? So this is the surge tank, and from the tank you again put a pump, and you keep this cooling water line active. Suddenly, somebody poured some hot water to it. A hypothetical condition. So your cooling water temperature should have been at ambient maybe 33 or 35 degrees C, maybe 300 Kelvin you count. Due to some manipulation, let's assume we don't know that this cooling water temperature has gone up to 350 degrees C. Okay, and your temperature you need to control is some 320 degrees C somehow. So when it is operating at the steady state level, okay, because of this sudden emergency, the temperature would start going up. Okay. Okay, now your controller will have to back it to the original level. So it would take some time, and this is the region of disturbance. Because of the error, eventually it would track down and finally it will go. So these are the two classic problems. So second one is the regulator or a disturbance rejection problem. The first one is servo or tracking problem. So what we are going to do here to get the overall transfer function. So if you look at the overall scheme, okay, there are two problems that you are going to do. One is the issue that is due to the set point. One is the issue that going to the disturbance. We know that the transfer function is linear in nature, so you could develop models corresponding to all two of basically two of this and kind of sum up because they are additive in nature. You see, this is adding over here, this is adding over here. So the overall transfer function of the system, which I will call it as GOL, it is the summation of okay your trajectory tracking or set point or something disturbance rejection. So I will say G servo and D regulator.
Hello, sir.
And what we have to, yeah, go ahead.
Sir, can I ask a question?
Definitely, please.
Sir, in the servo tracking problem, why aren't we tracking
Uh-huh.
the sudden
Yeah.
changes? Is it,
Go
is it
ahead.
because
Go ahead.
we
Yeah.
are uh, hello, sir?
Just missed you.
Sir,
Yeah,
is
I
it
could hear
because
you now.
we
Yes.
want it, or is it because we cannot track that sudden change in the process?
No, you're saying why this
Yeah,
regime.
yeah, yes, sir.
That your question?
Mm-hmm.
Yeah, because see, step change you can enforce, but see, it's like this, no? So you may not be able to do physically reach this. So if you could reach this, this is like a magic, no? So this is a change that you wanted to effect. And if you wanted to, if you feel that this you will get really like this in the field, it's magic. So today it's very things are. I think I got it. Why? Because so take a simple example. When you drive a car, okay. So you are driving at 60 km/h. Okay, and let's say your co co-passenger has told, okay, this is like you are driving in some highway. The minimum you could elevate the speed to 80 km/h. So what is the set point here? So look at here. So this is the set point, and you would maybe driving at 60 km/h. Fine, and you so this is the target, okay, and your speed may not, so you cannot be able to 100% match, so your speed may be slightly oscillating around that. So if you look at your speedometer, you will not be able to, unless you do what is known as the cruise control. I hope you know this. You can so the modern vehicle has this advanced, what you call, or maybe if you go abroad, this is a very common thing. You can lock the speed at a uh, particular set speed. Then you can take your leg out of the accelerator, so then it would do automatically. But otherwise, let's say you are just pressing the pedal of the accelerator, you will not be able to get the 60 km/h exactly, because it will be slightly, maybe 59, 61, who knows. So then you have been asked to make it to 80. Okay, so what will you do? You will start pedaling your accelerator more. Unless your vehicle is maybe BMW or whatsoever, so they say that even for them they would give you, so 0 to 100 km/h you will reach in 3 to 4 seconds. Agreed? Hello, am I audible to you?
Yes, sir.
Okay, so you have pedaled your accelerator at this point. So your speed would start increasing because it has to go from 60, 65, 70 and 80, no? 75, 80. So this would be incremental in nature, and you would reach here and you would see that this is not immediate. So if you put a perpendicular drop here, this perpendicular drop here, you see that this is the point in which you started effecting your control action, but this is the time you reach to the final steady state. This is quite common in irrespective of any system. This responsiveness would be, so this is the response. This responsiveness may be faster in aerospace application. So I would say look at the applications of control systems. Okay, so I'll say aerospace would be the most. Sorry. So this responsiveness, because you have to invest on such like minute hardware that affect things. The aerospace would be the fastest to respond because you cannot tolerate any single mistake, because it could reach to the, it could be fatal. Then maybe automotive, okay, and probably last would be chemical industry. Why? Because you can tolerate some time. Maybe even if it takes 10 seconds to reach, you might be able to tolerate. But applications like aerospace and automotives, this lead time should be very small. For instance, if you apply a brake, the vehicle should stop in 2 seconds. So what is the control action? That is like a step down operation. Okay, you are traveling at 60 kilometer, you wanted to bring it to 0. Okay, you applied your brake. Okay, and whichever however fast is the response, it is not immediate, it will take 2 seconds to reach here. Fine, but this step up and step down in temperature, why? Because this is also basically because chemical processes are inherently slow in nature. If you are started boiling the water, if you just switch on and if you start supplying whatever be the level of heat, it takes around 2 to 3 minutes to boil the water, even more. Agreed or not agreed?
Agreed, sir.
Okay, so this is the philosophy. Any questions at the moment?
So, sir, that curve represents the time that is required for the change to occur from
So
that
this
60
one,
or 75. Yes, sir. So, this white curve.
this one. Okay, so
Yes.
this is YSP versus time. Is that clarified?
Yes, sir. Thank you, sir.
Okay. So here also everything versus time. So T1, no? Here already I have time. Fine. So why time? We are dynamic systems. Okay, so you record everything with respect to some X versus T always. So we are always talking about dynamic systems. Okay. So now coming to the point that we were doing. So we have looked at the set point. Okay. We have looked at the servo problem of give me a minute. Okay, so we have looked at the servo problem last time. So servo problem, what would us we will have to assume that only it is, so at the moment this guy is okay. So because you can sum up, so you would take the first loop carefully, which is the set point thing. Then we will look at the second thing. So second thing means that the set point will not be there. So which I am going to mark with a purple thing. So this is, or the pink thing. So this is the servo, sorry, the regulator loop. While this is the tracking loop. Okay, so now, so overall problem is the summation of the disturbance rejection plus regulation. Sorry, the set point tracking. At the moment, we are not considering what is happening over here. So it is only the GPU, which is GP times U, is the output, because there is no YD here, so YU becomes Y. Okay. So now you can now write the thing separately. How do you get U? You will get U by multiplying error times GC times GV. Error times GC times GV. So, and what is error? Error, of course, is the difference between your internal set point, which I will call, which is the signal equivalent of the physical set point, minus the measured signal output, YSP minus YF. And you can also calculate what is this YSP? YSP is of course the physical variable times the the conversion factor. Okay, and so for the sanctity, we have put EM and GM to be different, but I think unless otherwise specified, you are free to keep it the same. Okay, so what is YM here? YM is Y times GM. Y times GM. Okay, so now what you have to just do is some rearrangement. What you are really interested is Y by YSP. So Y is on the left hand side, and you can see YSP here on the right hand side. So you take this Y also to the left hand side, do manipulation, so you will get Y by YSP. And so this is what this was the point where we were speaking last. So when you rearrange, you would see that in the, so it would be in the form of, okay, something, okay, some A by 1 minus 1 plus B. So the B part, so of course it would be 1 always. This B part would be the product of the transfer functions from, okay, GC, GV, GP, GM, which is fully inside this loop. And the numerator would be the forward path, okay, so which starting from Km, GC, GV, GP, Km, GC, GV, GP. So this is the forward. So the transfer function would contain forward element divided by the sum, the 1 plus the product of elements in the loop. So the loop here static, this is your loop. This is not by chance, this is by virtue of the the modularity of the system. You can check by yourself. I am not showing something from hand. This is not a hand wave argument. So now coming to the disturbance case, so which is the other case. So in this case, we would happily keep this guy to be 0. So y is equal to yu plus yd, and gp times u would be your yu, and d times yd, d times gd would be your disturbance rejection. And of course, you will have to now expand. Okay, so now gp gdd would stay as it is. Okay, so what is yu? Yu would be sorry, gp times u would be, okay, u would stay here, so it would be gc gv gp, gc gv gp, and ysp tilde minus ym. Ysp tilde is again km time minus ysp, and gp times gm times y. So we will keep this guy to be 0 at the moment, because there is no set point change. We are only looking at the disturbance rejection. So again, now you do rearrangement. So what you are really interested in y by d here. In the previous case, we are interested in y by ysp. So look at the interesting variable y by d, because we are looking at how disturbance is affecting the system. In the other case, we are looking at how set point change is affecting the system. So the y by d, if you look at, you would see that it's also magically you would get the same thing. So the numerator, when you rearrange y, so see y by gd, you would magically you would get y by d would is equal to gd, which is the forward path here, because gd to y it is only gd. So y, sorry, look at here. So from d to y only gd comes in the forward path, and things within the loop. Things within the loop is GC, GV, GP, GM. GC, GV, GP, GM. So 1 plus. So if you, so the fundamental aspect when you look in the transfer function, okay, you can see that the transfer function contains. So of course, this is the overall transfer function that contains the regulator component and the servo component. How you know that? So you say that this is YSP here, so it is servo. T here it is regulator. I have not done anything. I have just combined equation 20 and equation 18. So this is just a summation of 18 plus 20. Straightforward summation, which we can do. Why? Because they are additive. So see, this is just an additive operation. Okay, so now the key takeaway here is that, so if you are looking from y to d, you have to look for what is that in the forward path. The forward path is gd, that comes on the top. Regardless of your process, the denominator plus 1 by loop. 1 plus loop. What is there in the loop? gc, gv, gp, gm. And look at the second component. What is there in the forward path? Km, gc, gv, gp. Km, gc, gv, gp. And regardless of anything, denominator would be 1 plus OL. So GOL means that it is the loop transfer function, which is open, kept open kind of. So it would be GC, GV, GP, TM. So this celebrated result, which is this is an interesting result. This is known as Mason's gain formula. So if you have a loop, okay, and if you need to calculate the transfer ratio of two transfer functions, for instance, here in case y by ysp or d by y whatsoever, so it is calculated as the product. This is the product term, product of the forward path divided by 1 plus the product of every transfer function in the loop. So okay, so the key point, so this of course seems to be very interesting, but the only problem here is that this rule is applicable to only when your feedback loop has a negative sign in the comparator. See, this is a negative sign. So one is positive and one is negative. This whatever we have done is only applicable when we have this positive and negative sign comes in. You may see a particular case wherein both of these things are getting added up. So you will not be able to use this simplified formula as it is. Okay, so just we'll show an example, then I'll probably wait for some questions. So this is the overall transfer function. So now how are we decomposing it? Go inside and try to make simplification. So this is a loop and it contains positive and negative also. You can apply Mason's gains formula. So what are we going to do now? We are now going to replace the relation with E2 to this. How do we do it? Okay. Product of the forward transfer function, which is GC to G1. Okay. And divided by 1 plus product of all the transfer functions within the loop. So it is GC2 times G1 by 1 plus GC2 G1 GM2. Let me call it as G4, I think. So I replaced here G4. So this is simplified. Okay, similar to that you can add up, but you can see here this is so in that way we can keep on compressing it, finally make just try to relate between YSP and Y. But again, applying this Mason's gain formula is fully contingent on the fact that your comparator contains a positive and a negative. Otherwise, you will have to manually derive like what we have done like this. Okay, so before we go ahead, okay, proportional control and set point change. So we'll now the another aspect we are going to look at how the set point change and the disturbance changes are. So we have now looked at the general case. So now we look at two special class of controller, which is proportional and which is integral. So which contains two parameters Kc and here it contains Kc and tau. We are now going to look at how proportional controller and the integral controller respond to servo and regulatory problems specifically, and that is the remaining maybe 6 to 7 slides we will go. Before we go ahead, I can wait for any questions. Anything that is unclear till now? Is it all clear to all of you? Any doubt?
No, sir, it's all right.
Good. Perfect. Okay, so now as I told, so this is all general. You see, your GC is just GC. So now let's just give a parameterized form, which means that let's look at the problem with a very specific eye. So GC could be, now it can be P or it can be PI. You can also do the same analysis for PID, but only think that it becomes a little bit more complex, but you can do on your own. So this is basically an idea. So it can be P, PI or PID, or it could be anything. How your system responds to servo and regulatory problems for a specific control action. Again, so I'm not going to the modeling aspect of this problem. I think we have looked at it. So you have this is the disturbance line and this is the manipulated line. Okay, the process transfer function can be Kp by tau s plus 1, and I think for the disturbance transfer function also they are assuming it is going to be the same Kp by tau s plus 1 whatsoever. So the overall loop contains, as I told, your original set point, converted set point, controller, I to P, control valve, process, measurement. So I think for simplicity, the I to P is just a scaling factor KIP, and control valve is also just a scaling factor KV. So your sensor is also a scaling factor KM. So mind that if you have given with a specific dynamics, for instance, for a problem that you are going to solve, or when you are in the field working, okay, and you have been told that the sensor is having first order dynamics, you will have to take Km by tau s plus 1. The valve has second order dynamics, you will have to take Kb by tau square s square plus 2 theta tau plus 1. This, unless otherwise not given, there is no harm in taking them as some scaling factors because you don't know the dynamics. And just so, of course, in this problem, we are just taking it all for the simplicity. But again, mind that if you have been given with a specific information, your ITP dynamics are first order. So it would be KIP by tau IPS plus 1. You have to use this information. At the moment, we don't have to. So it is for anyway for illustration purpose. So now look at the transfer function, how it is going to be the forward, and so let's look at the set point change. So the numerator would contain Km, Gc, Kp, Kv, Kp by tau s plus 1. Km, Gc, Kp by tau, K. So, okay, so we are assuming proportional control. So your Gc becomes Kc alone because there is no integral component, nothing. Okay, so Kc, Kp, Kc, Kip, Kv, and Kp by tau s plus 1. This Km is coming from here. So it is, please note that it is not written according to the sequence. And the denominator would contain 1 plus all these guys. Gc, Kip, Kv, Kp by tau s plus 1 and Km. 1 plus all these terms. Okay, so now what I am trying to say is, consider this as an exercise. You can just check. Okay, this could be also written as a some general constant k1 by tau 1 s plus 1. So you see that your tau is different and your k is also different. So your k1 will become this particular form. KOL by 1 plus KOL, but KOL is the product of all these terms, and tau 1 is 1 plus tau by 1 plus KOL. Do at your leisure, you will be able to get it. So the point what I am trying to say is this would be another overall dynamics with the first order with this constant has a different meaning, which is the product of some other terms. So what we are going to do here for us, so we are now going to look for a set point change. So set point change, what we will do, your uh, your previously at t, let's say at t is equal to 0, you have effected a set point change over m. So this is 0 and this is m. And we are going to calculate this offset, if there is any offset or what. So this is your original variable, which is ym, and this m, you need to track m. So any error from m to this ym is your set point. So m is the required value that you have to reach, and what you call eventually, so what you are going to get would be k1 so why are we saying it is k1 minus m? See, this is like a first order system, so k1 minus m. So when you take the integral, which means that when you integrate and when you get the time domain, what are you going to get? 1 minus e raised to minus t by tau 1 s plus 1. So when t become infinity, your final values. So I hope you are understanding what I'm trying to say. Let me write it again. fine. And so at t is equal to, so this is the set point YSP, and you have hiked it to m 0 whatever. So this was this this is your m. Okay, so the error so the final error that you would like to get would be, okay, m minus, and you, this is your output, whatever maybe, and let me draw a green line as your output, and it might go like this. I'm confidently saying it will not reach. Why? Because your proportional control are known with offset. So why it is known with offset? So you have seen y by ysp is k1 by tau1 s plus 1, or whatsoever be this new k1 and tau. So what, when you integrate, so y of t would be, so let's say if you do a step change of m, what you are going to get would be m times k1 times 1 minus e raised to tau1 s tau1. So when t tends to infinity, this term would go. So eventually what will you get would be m times k1. The offset is now m minus, so this final value is not m, it is just m times k1. The offset is m into 1 minus k1. So it is m into 1 minus k1. This is what we have written over here. So now look at, so eventually what are we saying? If you have a proportional controller, if you do a set point change, you won't reach m, but you will only reach a 1 minus m into 1 minus k1. So there is a offset. So let's say look at your disturbance. Let's look at the disturbance rejection problem. Then we will have the forward path would be kp by tau s plus 1. Of course, the denominator path would be the same thing, 1 plus kc kip kv tau ts plus 1. This whole thing, which we have been written as 1 plus KOL by tau s plus 1. So this you would be eventually taking up a new form K2 by multiplying the all constant K2 by 1 plus tau s plus 1. So here also what you would really see that, so it's a regulator problem, disturbance rejection problem. So you don't have any set point. So you have to maintain the desired trajectory. You don't have to change, but there is some disturbance happen and finally it moved away. So you have to calculate the offset as the difference between K2 m minus, rather 0 minus K2 m. So again what you are going to get is that the take home message is that if you had a proportional control to the to control the disturbance rejection in a closed loop system, you would be having an offset of K2m minus K2m, where m is the set point value, K2 is the transfer function, the simplified transfer function in the numerator. So, so now look at it is if it become PI controller. So we are only looking at the disturbance rejection for the PI control. So just to get a feel how it is going to be different. So the difference that your KGC become now KC times 1 plus tau I, 1 by tau is. So when you substitute it and when you do the manipulation and when you calculate whatever integration, you would see this following. So forget about, so you can try the steps. The integration would give you a complex thing having an integral zeta 3 times t and all. So what would happen when t tends to infinity? You substitute the t, this whole term, this exponential term will evaluate to 0, which essentially means that the whole thing would evaluate to 0. So what would be the offset in this case? 0 minus the response, which would give you 0. So the take home message, if you add an integral component, the PI control, due to this additional integral component, the overall system offset has been removed. So this is also true when you do tracking, which you can independently check. I hope in the textbook they have shown an example. So here instead of k1 minus m minus k1, you would see that m into 1 minus 0 you would get. Okay, which essentially means that eventually you will be able to reach the set point m. So if you add an integral control, which is addition to the proportional, you would see that there is 100% offset elimination. So this is the take-home message that I wanted to say here, and I can wait for a couple of minutes if you have any clarification. Any clarification at the moment? So this is absolutely, so the analysis is absolutely similar. So you have, you know, what you have to do. You have to calculate some transfer function g by g1, which is the transfer function of the set point or even the disturbance. Then you have to do the inverse. So we have doing this from the maybe the in the first chapter onwards. But your transfer function here is the fully closed loop transfer function. So you will have to take up the all factors and join them together. That is the only thing that you're additionally doing here. Rest all you have already learned. So we are now kind of imparting that knowledge on the closed loop transfer function. If you want to pedagogically think what we are doing. So we are not learning anything new in terms of the responses or action, but we are only learning new in terms of how to do this reduction, how to reduce this complex loop transfer function to a simplified transfer function. First, all you have learned pedagogically, it is just imparting those information onto this. Any doubt at the moment? Is that all clear? May I go ahead?
Yes, sir.
I hope. Shruti, you want to saying something or it's all fine?
Sir, I said it's clear.
Okay, so now of course, so till now what we have learned is kind of imparting something on the top. So what we are going to learn is slightly new, but you have learned some part of it. So we have now looked at the responses. So we can also look at the stability in the sense that if you have made this complex control system and you have put a step change into the set point or in the disturbance wherever. So input set point, this can be at step in the set point side or in the disturbance side. Now we need to look whether your system is stable. So how do you evaluate your system is stable? There are various definitions of stability. See, so there are various definitions of stability. So you look at the premise, okay, you did an input change. So for instance, it was normal, you stepped up. This is one input change. This is like a step input change. It can be at the disturbance side or the set point side, wherever. Or you might do a ramp change, or you might do something. So the simplest stability, okay, the simplest definition of the stability, as I told, there are various definitions of stability. Somebody who is interested, I don't know if you are some who has taken real analysis class in mathematics. I don't know if someone has taken. You would be surprised to see there are around 20 to 25 definitions of stability. So we don't go into all that. So we will look at the simplest form of stability. So what is the simplest form of stability? You have injected, okay, this is your loop. Okay, so you have various components. I'm not marking though. Oh, I'm sorry. Sometimes it's annoying though. Wait. Cool. So this is your loop and this is your output, and I will say maybe I can put a D also here. So this is your D, you have a transfer function, this is your Y, and this is your comparator, this is your YSP, inside whatever maybe, I'm not going to share. So the simplest form, you are either introducing some change here or change here, which is the set point side or in the disturbance side, and The simplest form of stability, what we can say, is by observing Y. You put a binocular or whatever, put a sensor and start looking at Y. The simplest definition says it is bounded input, bounded output, which essentially means that if you send input which is bounded, okay, your output should also be bounded. It is a very fair definition. So you are doing a change which is bounded. So see, mind that the ramp is not bounded. It can go up till, but unless if you clip at some point, it is bounded. But step is bounded because it is a boundary. Sinusoidal is also bounded because there is a boundary. Ramp, as you told, it is not bounded unless you clip at some point. So the definition, the BIBO stability or bounded input bounded stability says, which is quite, it's a fair deal. It's a fair definition. You do a change which is something bounded here, which essentially means that you made a set point from 1 to 2, very bounded. You're not changing from 1. If you are changing from 1 to infinity, it is an unbounded change in the input. Then you would prone to get an output that is unbounded. But if you make a bounded change, 1 to maybe 200, maybe 1000, all bounded, okay? If your input is bounded, essentially means that your output should also be bounded. Or your output bounded essentially means that your input is also bounded. So this is one of the definitions of stability. As I told, there are 20 to 25 definitions of various specific aspects of stability. So this is called bounded input, bounded output stability. Okay, so now I think I have 2 minutes. I will just show something which you can of course look at detail in the tutorial class. How to check the bounded input, bounded output stability. I think I will take 3-4 minutes. Please bear me so that then we'll be able to take up that in the next tutorial. Otherwise, we may not be able to. Just give me a minute. So it can be displayed. Quite interesting. There was a problem in opening. Okay. I think probably my device don't want me to teach that, but I can tell you the thing. So how do we calculate it? So the definition of the stability is strongly tied to the denominator transfer function of the GP1 plus by GP2, whatever, maybe y by ysp or y by yd, whatever. So it is highly dependent upon the roots of the denominator transfer function. This we have learned also. So so of course these are all polynomials. The polynomial, where are the roots lying on the polynomial, that makes the whole system stable or unstable. Okay, so if the roots are, so let's say this is if you plot in a quadrant, if you put, so any roots on the left hand side of this what you call this quadrant makes the system stable. So if it is on, oh, give me a minute. I hope now I may be able to open it up. Okay. Okay, let me continue with my writing for a minute, then I'll stop. Okay, so roots are on the LHS, it is always stable. So if it is on the axis, you would see the response is smooth. Okay, if it is on the if you have some imaginary component, you will still see that it is oscillatory but stable. But if anything on the right hand side is unstable. Why? Because when you take the inverse, you see here instead of e raised to minus t, you would see a positive t, which essentially means that over the time growth, this become unbounded. Okay, so to check, so the simplest case, okay, so if it is like s square plus 2s plus 1, you can check the roots and find out. Let's say your denominator transfer function has 10 roots, s raised to 10 something something like 2s plus 1. This is very difficult to check because you have to calculate the roots of this 10th order polynomial. So to do that, there is something known as Routh array test. I will stop here. So we will solve that problem directly in the tutorial. It is a simplest way to check where is the roots lying in. This is by means of a method known as Routh array. So we will stop at this moment and we will take up this problem in the next class maybe. I am so